Now in this video, we will study about the meter bridge or slide wire bridge. Now meter bridge is a device which works on the principle of Wheatstone bridge, or you can also say that the meter bridge is it's a practical application of the Wheatstone bridge. Now in the previous video, we all have studied what exactly the Wheatstone bridge was. If you remember, the Wheatstone bridge was an arrangement of 4 resistors which were arranged like this. Say this was resistor P, this is Q, this is R, this is S, and if I connect a galvanometer between these two terminals and the other two terminal is connected across a battery terminal, then what we see over here is that if P upon Q equals to R upon S, then the galvanometer does not show any deflection. Now something similar happens over here. Now Wheatstone bridge is nothing but a long 1 meter wire. Say this is a long 1 meter wire, and the other ends of the wire are connected through a copper strip. Here you have a copper strip which is L-shaped. At the other terminal also you have an L-shaped copper strip, and in between you have another strip. This entire setup was basically set up over a wooden box. Now between these two terminals, that is this and this terminal, one resistance box is connected, and between these two terminals, this and this, an unknown resistance is connected. Say that unknown resistance is X. And from the middle terminal, here you have a wire which is connected to a galvanometer which is connected to a jockey. And these two terminals are connected to battery, which is basically giving supply to this entire meter bridge apparatus. Now let's label the terminals. Now let's say we call this terminal as A, and at the same time we'll compare this meter bridge circuit with the Wheatstone bridge circuit. Now this is terminal A. Here this is the A terminal. This is terminal B. Over here this is a B terminal. This is terminal C, which is here. And this terminal where you are seeing, this is a D terminal. Now as you can see from here, that between the terminals A and B, resistance P is connected. So over here, the work of this P is done by this R resistance box. So whatever resistance A we take out from the resistance box, that works as a resistance P. Now similarly, between the terminals B and C, the Q resistor is connected. Here the work of Q is done by this unknown resistor X. Between terminals A and D, we have a resistance R. Over here, this resistance R is the resistance of the wire AD. And the terminals, between the terminals C and D, we have this S resistance. The work of this S resistance is done by this remaining portion of the wire. Now say the length of the wire AD, say, is given by L. Then the DC length would be 100 minus L centimeter. Okay, this entire length would be in centimeter because the meter bridge has this wire AC which is of 1 meter length, that is of 100 centimeter length. Okay, now what we do over here, once the circuit is made and this key is closed, we basically look for the null point. Null point means the point over this wire where the galvanometer does not show any deflection. Now if the galvanometer is not showing any deflection, that means there is no current which is flowing between the terminals B and D. That is between these two terminals. Now this condition, we say that the bridge is balanced. Means at balanced position, galvanometer does not show any deflection. So here we say that this is a balanced Wheatstone bridge. Now, if I write the same P upon Q equals to R upon S for this setup, how we can write that? Now, instead of resistance P, we are writing the resistance P itself, because here both the resistors we have taken it as P. Now, instead of Q, we are writing X over here. Instead of R, we have the resistance of the wire AD, and instead of S, we have the resistance of the wire DC. Now, resistance of the wire AD can be written as resistivity of the material of the wire, length upon area. Area, small a, is the cross-section area of the wire. Similarly, RDC will be the resistivity of the wire, length of the wire, which is 100 minus L, upon cross-section area A. Now, if I take the ratios of these two resistances, RAD upon RDC, here we see that this rho and rho gets cancelled, A and A get cancelled, and what we get over here is L upon 100 minus L. So, from this relation, I can write that P upon X equals to L upon 100 minus L, or I can write X equals to P into 100 minus L upon L. Now, this is the relation which we get, or this is the formula which we get, which helps us in finding the unknown resistor X through this meter bridge setup.